everyone. Welcome to our special seminar series on survey and space exploration, SSSS. First started with Nash's great idea to center seminars around special themes over a short period of time, with one important topic being surveys and space mission. Some special investigation were carried out during our winter solstice party, and they revealed that this idea actually resonated very well among citizens. So your visitor committee thought it would be great and very exciting to make January special, not because of the pandemic situation, but the opportunities to have great speakers coming to us from all over the world to inspire and engage us with the various observational sides of the science that we are all interested in. So we made this surveys and space exploration series for us to learn about individual survey or space mission, as well as their synergies. So on your screen here, you can see the poster and the program we sent to you all with talks on different topics. Please feel free to provide feedbacks and make suggestions to your visitor committee, which including Nash, Ted, Sinew, Dylan, Dick, and me. I will now hand it over to Ted to introduce our very first speaker for this series. We're honored to have George Seabroke. So Ted.
Yeah, so it's a great pleasure to have George Seabroke here to talk to us today. So George finished his PhD in Cambridge in 2007, supervised by Jerry Gilmore and Wyn Evans. He then moved on to join the Centre for Electronic Imaging in Brunel University before moving the entire group to the Open University in 2008. And then since 2010 has been at MSSL and has really been focusing on the development and production and actually now the implementation of the Gaia RVS spectrograph and the data that we're going to get from that. And as we all know, the RVS spectra are going to come with Gaia DR3 in the first quarter of this year. So it's very exciting that we've got George to talk to us about all about that data and all things Gaia at this point. So thanks, George, and looking forward to the talk.
Yeah, well, thank you very much for the nice introduction. All correct. Yeah, and yeah, thank you very much for the invite. I'm very honoured to be your first speaker of the SSSSSSS. I think too many S's there that I've said, but yeah, so it's sad not to see you in person, but I've also kindly been invited to the Gaia DR3 hike, which is happening in Canada, hopefully COVID permitting, in the summer. So hopefully I'll get to meet many of you in person then. So let me, but in the meantime, let me share my screen and give you this virtual presentation on Gaia. So yeah, can you see that okay?
Yes.
Yeah.
Okay.
Okay, so, oops. Yeah, so I've hopefully not too ambitiously given my title of the talk, the Gaia Revolution. So I'll hopefully try to convince you that a revolution is happening in astrophysics, and the Gaia data is very much a big part of that. So the outline of my talk is to remind you about Gaia as a mission very briefly, and then I'll look at what came out in Gaia DR2, which has been superseded by Gaia's early data release 3, which came out at the end of 2020. So I'll look at that and then look forward to the full data release, which, as Ted said, is coming up in a few months' time, so the second quarter of this year. So it will be an unashamedly biased towards the radial velocity spectrometer. So this is the instrument on Gaia that I work with and know the most about. Of course, Gaia covers so many different aspects. You could probably do your entire seminar series on a different aspect of Gaia each week and fill your schedule quite comfortably, but hence the reason to try and focus in on the RVS data for this talk. So the Gaia mission in a nutshell, this is it setting off. She was launched on the 19th of December 2013, so we're over 2,700 days into the mission. So the launch was in French Guiana in South America, and I was fortunate enough to be there. So this is about a minute after that launch, seeing Gaia already in space at this point, and had a colleague of mine shouting at me saying, George, just stay there. And I was like, no, shut up. I'm trying to watch the launch. He said, no, I've got a great picture. And so this is the picture that she took, and I'm very glad she did. So we're by chance so recreating the logo here, and this is, you may just be able to tell, the logo on the fairing that protected Gaia, all folded up on top of the Soyuz rocket, is here, and it's a girl sort of waving at the stars, and that's almost what I'm doing there with this picture. So after launch, it was inserted into orbit around L2, so that's the Lagrange point 2, illustrated in the plot here. So that's the gravitational saddle point between the Sun and the Earth, and also the Moon. And so Gaia is a satellite of the Sun in its own right. It's not going around the Earth. It's being dragged, effectively dragged around the Sun by the Earth. Following this solid line going around here. So you would have already heard about L2 from many other missions, the most recently being James Webb, but I'm reliably told there's a lot of space out there, so presumably they're not bumping into each other out there, that's or getting in each other's way. So what Gaia does is astrometry, photometry, and radial velocity. So I'll describe a little bit more about what all of those mean. So here's the focal plane. So it's on the ground, and for scale is a technician working on this in Toulouse in France, where the final integration of all the detectors happens. So each one of these CCDs was built in by a company called E2V, now called Teledyne E2V, so a British company which has been, since the launch of Gaia, bought out by the American Teledyne company. And it was a French company, Astrium, as it was so called then, that made Gaia, which is now part of Airbus. So Gaia was the largest, at the time of its launch, it was the largest focal plane to be launched into space and on the ground. So it's still the largest focal plane in space by the number of pixels, which is nearly 1 billion. So there's nearly 1 billion pixels measuring more than 1 billion stars, which cost around €1 billion, very roughly. So lots of billions involved. As I say, yeah, there's the scale of it next to here. The different CCDs are the sky map of CCDs here. So Gaia doesn't actually have a pre-selected input catalog of stars to record. It records everything that moves, and that's brighter than a particular limit, which I'll show in a moment. So it is actually recording asteroids, distant galaxies and quasars, as well as stars, but it predominantly has been designed to measure point-like sources, the majority of which are stars within Gaia's magnitude range. So it does the astrometry with all of these CCDs here, and we have the colors that are coming from the blue photometer, the red photometer, and the 12 RVS radial velocity spectrometer CCDs here. So I should say that since Gaia's launch, the largest focal plane is now Pan-STARRS, I believe. So it actually beats Gaia in terms of the number of pixels, but I believe Gaia is still the largest number of pixels to be launched into space. So what gives me the right to come and talk to you about Gaia? So it all started back in back on the left-hand side here, when Gaia was still an acronym, so with all the capital letters there. So Global Astrometric Interferometer for Astrophysics. So you can tell from the graphics here that this is quite old. So this is from the proposal back in 2000. So it's no longer, so the interferometer part of the design is no longer used in what was actually manufactured, but the name, because it was such a long lead mission, the name Gaia was kind of fondly looked upon, and so it's been kept as a name, but now capital G and lowercase letters here. So my boss, Professor Mark Cropper at the Mullard Space Science Laboratory, proposed to build the radial velocity spectrometer at MSSL. So the actual proposal to manufacture RVS wasn't successful because in the end the sensitivity of the focal plane was such that it was felt that all the instruments should be built by the same company, so Astrium, later Airbus, and integrated by that same company. Nevertheless, the design work that occurred meant that MSSL was able to win the contract to test all 106 flight CCDs plus many more spare CCDs. And so here's a vacuum chamber with its lid lifted off, the space for 4 CCDs to be tested simultaneously, but only one actually there. So hopefully Jennifer has told you all about how lovely MSSL is. It's actually an old country house in the Surrey Hills with London back over this way. But of course we haven't been there for a little while. But hopefully, if you'd ever like to come and give a talk at MSSL, please let us know, and we'll get you in virtually, and then COVID permitting, maybe you could come and visit us one day as well. So so all the detectors were tested by MSSL, and Mark Cropper, my boss, continued his involvement with RVS and plays a major role in the proposal to write the software to process the data coming from Gaia, specifically the radial velocity spectrometer spectra. And so that's my job from 2010, has been working on the pipeline to process this data, and now I'll show you the results that have come out in the previous years and what's still to come. So in terms of what Gaia is, it's an optical mission. So here are the pass bands here. So Gaia's optical CCDs are basically from around 300 nanometers to nearly 1,000 nanometers, and there's also a blue and a red photometer, which I'll also show in a moment. Oops, sorry. And in terms of the depth that Gaia can go to, it's G magnitudes, as they're called, which are very similar to the Johnson V visual magnitudes. So it go down to fainter than 20th magnitude, as seen here. So the radial velocities don't go as faint. So for DR2 and EDR3, they go to about 13th magnitude in G. So why are we doing it? Well, we're making a 3D census of the Milky Way. So the idea is to try and understand how the Milky Way formed and its evolution and its assembly history. And to do that, we need to take all these precise measurements. So the idea is to measure, even measuring over 1 billion stars is only roughly 1% of the stellar population of the Milky Way, but it's hoped that it's surveyed in such a way that that it minimizes the biases in how we observe those stars, and so that it's a representative 1%. And so from that we can infer how the Milky Way has formed and evolved by comparison with models. So I'd like to be able to tell you how it's all done, but I'm afraid time will be against this if I do that. So I will focus on the data that's available in my remaining time. But of course, I'll ask how we actually make the measurements, of course, later if you like. So so this is a slide that summarizes Gaia's data release in DR1, which was back in 2016, DR2, 2018. And the different parameters here. So when we talk about 5 astrometric parameters, we're talking about the position at a reference epoch. So the reference epoch changes slightly for each data release. For example, in DR1, I think it was 2015, DR2, 2016. So these are the first 2 parameters so that we're able to provide a position at a particular reference epoch, which is essentially arbitrarily chosen. The next 2 parameters are the proper motion. So that's the dotted blue line here. But of course, we don't actually see the proper motion in the sky. What we actually see is each star traces out a line similar in the plane of the sky to this red line here, so this sort of helix-like shape. And so this is happening because of the parallax. So this is Gaia seeing one star from one side of its 6-month orbit, is 1 year orbit around the sun at one point, and then 6 months later it will have seen that star has moved. And so continuously following how that star changes its apparent position as Gaia's motion goes around the sun gives you this loop back here. And so without proper motion, you just see a star tracing out this ellipse. But with the proper motion, so this is actually the physical motion of the star through the galaxy projected onto the plane of the sky, you can see that this helix shape evolves with time. And so by fitting a model that describes these 5 parameters to all the measurements, so we'll measure, Gaia is continually scanning the sky, and so we'll measure the time as which it sees particular stars, and then an astrometric model will actually predict according to, it will try lots of different parameters for these, it will try lots of different values for these 5 parameters and predict the path and predict the time of a star's transit across Gaia's focal plane, and thereby the model and the data meet, and so through essentially a very complex chi-squared minimization, we're able to find the parameters for these, the values for these 5 parameters. So that's, as I say, one Gaia astrometry in one view graph. There's a little bit more to it than that, but in the interest of brevity, I'll keep going. So so I've talked about a revolution. So Gaia's predecessor, the satellite called Hipparcos, which is also a European mission, measured parallaxes for about 100,000 stars. And Gaia was able to use those measurements combined with its measurements and actually measure the parallax and the proper motion and the position for about 2 million of these stars. And so I should say that the parallax is key here in terms of being able to, you invert a parallax in order to be able to measure a distance to a star. And of course, distance to a star is a very fundamental parameter in order to put lots of other things on an absolute scale. So so from this 2 million here, we jump up to 1.3 billion sources with the full 5-parameter astrometric solution. And so this jump here is really the big step change in astrometry, which has really precipitated this revolution. So part of that as well is the measurement of radial velocities. So we go from none in DR1 to 7 million in DR2. At the time, there was around, I think the record then was about 4 million ground-based radial velocities. So Gaia took the record, and this was from a Chinese telescope, LAMOST. LAMOST have since come back and published around 9 million, but I'll show you Gaia is hoping to retake that crown in the next couple of months. So in Gaia DR2, those 7 million radial velocities produced this first all-sky radial velocity map. So previously, radial velocities had been measured from the ground from different instruments, obviously needed for different hemispheres on the Earth. But measuring radial velocities from space is the first time you can make an homogeneous map of the whole sky with radial velocity. So this is the line of sight motion of these stars. So with the redshift of these stars, the stars moving away from you, and blue, the stars coming towards you. So you can see that we've got a differential galactic rotation going on here. So the power of Gaia is to put all these measurements together. Oh, I can see my screen's telling me there's a question in the chat. Is that?
Juna says she would quibble slightly with that claim, but I'm not sure which claim it was.
I've made many claims.
Yeah, in terms of the uniform radial velocities, of course, like from the ground, and having, you know, in SDSS-4 with a jump of a kind of same spectrograph to the southern hemisphere, you know, the scale is quite different, but the uniformity, I think, is what we can get there. But of course, you've got the atmosphere, etc. So that's why I said I would quibble slightly instead of reject entirely that claim.
Okay, that's actually a good point. I'll retract my claim. And yeah, no, thank you for the clarification. Yeah. So the Power of Gaia is putting all these measurements together. So the simple plot is illustrating how that is done. So the parallax of each star essentially gives us the distance between Earth and the star. That proper motion gives us the distance when combined with the proper motion can give us an actual physical transverse velocity in the plane of the sky. And so the reason for going after the radial velocities is to get this orthogonal component of the velocity here. And so when you've got these two components here, then you've got the full information to describe the three-dimensional space velocity of the star, and then you've got the full information about how that star is moving, and it's that can be used to good effect. So some of the Gaia Dr2 Science highlights bias towards usage of RVS data are these two Nature papers here. So they both use astrometry and the radial velocities from Gaia Dr2. So first of all, the plot on the left here is taking the vertical velocity, the vertical space velocity with respect to the galactic plane. So this is how stars are moving away and towards the galactic plane, and then the distance below and above the galactic plane. Oh, sorry. So if you color code these velocities if you color code this space with v phi, which is the azimuthal or rotational velocity with respect to the galactic center, then you end up with this really strange kind of snail shape here, which was really an unexpected local phase space structure. And so it's been explained as like essentially a ripple. If you throw a pebble into a pond, you get a ripple going through the pond, and this is in effect what we're seeing in phase space. And it's allowed a new field of galactic seismology to start up, in the sense that the Sagittarius dwarf galaxy, which the Milky Way is cannibalizing at the moment, plunged through the galactic disk on the other side of the galactic center compared to us, and it sought to have created these ripples, and looking at simulations of how these ripples might occur and propagate across the galaxy. You can predict that something perturbed the galaxy at around oh gosh, I've forgotten the timescale of when this happened. A few billion years ago. Should we say apologies? Someone will be able to tell me, I'm sure. And then from other information from the Sagittarius dwarf galaxy itself, the timescale from the estimates of when that galaxy was thought to plunge through the Milky Way disk on the other side of the galaxy, it seemed to be consistent. And so this could be a way of so here we can connect the Sagittarius dwarf galaxy plunging through the disk on one side and seeing an effect on the other, potentially. So this is still being investigated, and but the power of being able to use how stars are moving as a kind of seismology for measuring the Milky Way and inferring what's happened in the past is very exciting. Secondly, is the discovery of Gaia Enceladus. So this was a merger that led to the formation of the Milky Way's inner stellar halo and thick disk. So the plots here are the plot on the in the middle here is using the radial velocities from Gaia's RVS, a similar discovery of this galaxy was also made with using astrometry and other data, and it was called the sausage. So this is sometimes called the Gaia Enceladus sausage. So this is using these space velocities that I referred to. So this is the essentially the rotational velocity on the x-axis, and a combination of the radial motion with respect to the galactic center and the vertical motion with respect to the galactic plane combined together. So this is in fact a tomb ray diagram, and so this is the data from DR2. Oops, excuse me, on the left, and a simulation on the right. And so this is a simulation of quite a large galaxy that merged with our own, and the debris from that merger produces these characteristic shapes in this particular space, which allowed us to infer that is what we're seeing in the data. And so and this was really, I think this result is really the, or I should say that I also made a tomb ray diagram of the, of the data and saw something happening here, but I can put my name to a long list of people who saw tantalizing glimpses of this data and this effect, and basically seeing Gaia Enceladus in their own data goes back actually probably more than a decade, but it's getting enough data from Gaia and putting it all together and having the sufficient simulations to infer what happened was really what happened in the breakthrough with DR2. And so this result was really what Gaia was built for, really, to constrain the assembly history of our Milky Way, and this is a major piece of that puzzle. So the impact of Gaia is illustrated in the plot here. So this is paper count on the y-axis against year on the x-axis. So Gaia starts modestly. Sorry, I should say this is for ESA missions, and so Gaia is added on here. So you can see Gaia really is increasing after DR1 in 2016, and then 2018 with DR2 it's going up, and then still going up as all the analysis of DR2 is happening. And so it's actually, at least for the moment, overtaken Hubble in terms of its paper count being the most productive scientific mission. And hopefully I'll convince you with all the rich data that's already out there and is yet to come, that this trend will keep on going, but we'll watch this with interest. So to explain the data, the reasoning for Gaia's data release 3 being split into two parts, the early part, which is already released, and the full part, which is yet to be released. I'm showing how Gaia's Data Processing and Analysis Consortium, or DPAC is the acronym, is organized. So the astrometry comes from Coordination Unit 3 here, and the photometric processing is in CU5, and spectroscopic processing is in CU6. And so this is the box within which MSSL and the team of software engineers that I work with are contributing to this particular pipeline. And for my sins, I'm the deputy manager of this processing unit. So the early data release was focusing on what we call the upstream data products, which is the astrometry and the photometry. So this intermediate data update is the large cross-match procedure which takes place, which matches all the individual measurements to their particular sources. And then CU9 is the archiving and the validation of the data holistically as a whole. So the contents of EDR3, Gaia's early data release, are now shown here. So so in terms of numbers, the release is more of an incremental increase as compared to a revolution that I described before. So the 2 million to 1.3 billion to nearly 1.5 billion is a bit more of a modest increase, but each data release in terms of the astrometry and photometry from now on is expected to increase those numbers as the processing improves. But it's also the precision and the control of the systematics which is expected to improve as well. So I should also show that the G photometry, the G magnitudes have increased from 1.1 in DR1 to nearly 1.7 in DR2 to a little bit more than 1.8 billion in EDR3. And then the photometry that comes from the blue and the red photometers wasn't included in DR1, but both contributed about just shy of 1.4 billion measurements, 1 billion sources with this color information, and that's increased to about 1.5 billion in EDR3. And then the radial velocities have actually decreased slightly from DR2 to EDR3. So that's because these radial velocities are actually part of these are actually the DR2 radial velocities, which have been included in the archive because of the usefulness of combining the radial velocities with Gaia's astrometry. So it was felt like it was beneficial to have those radial velocities in the archive at the same time. So these radial velocities are based on the DR2 astrometry, and so there was a number of cases. So there's 14,800 sources which haven't been propagated. So the main reason for that was the mismatch in the DR2 astrometry and the EDR3 astrometry, which meant an unambiguous match couldn't be made. And we also took advantage of given that we were copying over DR2 to EDR3 to clean up some of those. So 3,000 radial velocities were excluded because they were found to be erroneous in DR2. So that's the bit that I led in as part of the EDR3 effort. So in terms of the astrometry, so on the left here we've got the parallax. So this, from inverting the parallax, you can get the distance, but that comes with its own biases, and there is a paper with EDR3 which I'd encourage you to read when using these parallaxes. So here this is in terms of micro arc seconds, which is a bit of a crazy unit to consider, and so there's an analogy which I'll show you in a moment. So but this is to show you the DR2 formal uncertainties in parallax in blue. In green is the EDR3 one, so you can see that in particular the systematics at the bright end, which are improved, and then it's just beating down the Poisson noise at the end, at the faint end, with repeat measurements, which is helping at the faint end. And then DR4 and DR5 have been extrapolated in this plot here. So on the right hand side, it's proper motion. So this is micro arc seconds per year. So you can see the improvement from DR2 to EDR3 and then extrapolated here again. So the analogy is that if an Apollo mission manual was left on the moon and Gaia was observing it from the Earth, then a micro arc second would be a full stop at the end of a sentence in that manual, and so that's so that's what a micro arc second is. So for DR2, you can basically tell that there's a manual there. For EDR3, you can tell, is there a figure on that page? And then ultimately, the aim with Gaia is actually to be able to read that manual, because I know, until someone goes and gets that manual from the moon, I don't think actually a manual was left on the moon. But if it was, they could go get it, or Gaia could read it, but it won't, because it's just an analogy. But hopefully that gives you a little bit of an idea about the incredible engineering and precision that goes into these measurements. So it's a combination of Gaia's incredibly stable platform at L2, a stable space environment, and the repeat measurements and the data processing on the ground that allows this to be possible. So in terms of photometry, the white light, the G magnitude is just no filter. That's just like hitting the detectors, as I say, without a filter. And then the blue and the red photometers are shown here, and they are producing their own magnitudes. And so you can see, in terms of the improvement from DR2 to EDR3, we're starting to approach milli magnitudes in terms of the precision at the bright end. So then for the radial velocity, so here's just a picture of the Gaia's radial velocity spectrometer, and the radial velocities that were rejected from EDR3. So the most of the high velocities here were excluded as being spurious, leaving us with a more realistic distribution for EDR3. So with each data release comes performance verification papers, and the idea of these is to illustrate the quality of the Gaia data and do some essentially be a science primer for the community. So these are the titles here. I'm afraid in terms of time I won't go through them, but this is something to look out for Gaia DR3 and the announcement of the performance verification paper titles will give you an idea of the data and the science verification that's gone on within DPAC, and so those should be coming out quite soon. So so back again to showing you how Gaia early data release was organized. So I've put a dash line around the C6 box because it wasn't really new data, it was old data. So the new parts were the astrometry and the photometry. And now looking forward to the Gaia's full data release, it's now we're looking at new data from C6, so from the RVS and all of these processing units here. So these are, the downstream processing units. So the complex object processing. So I'll talk about binaries in particular from here, but this also includes solar system objects and galaxies. And then the variability analysis. So this is time series analysis, and then astrophysical characterization of the stars in CU8. So this is what's coming out in the full data release. So these numbers are pretty fixed now, in that the validation of the full data release has been happening in DR3, and so these numbers aren't expected to change very much. So now you can see that we're going to get quite a big jump from the 7 million radial velocities are going to jump up to around 33 million radial velocities in the full data release. And I'll explain a bit more why that's happening in a moment. We're going to have more than 100 million BP and RP spectra, a million RBS spectra. Source classifications is really jumping up from previously. Sorry, come back. So there'll be object classifications for the first time. The sources with astrophysical parameters. This did happen for 100 million plus sources in DR2, and that's going to increase to about 500 million in the full DR3. And then for the first time, we'll have solutions for non-single stars, galaxy morphology, solar system objects is really jumping up by an order of magnitude. The spectra for asteroids, and a particular survey towards the Andromeda galaxy. So I'll spend the rest of the time just showing how the radial velocity spectrometer data is contributing to these data products that are coming out in DR3. So yeah, so this is the data from CU6, the spectroscopic processing. So so in DR2, we limited ourselves to the GRVS magnitude. So that's the magnitude native to the radial velocity spectrometer. So that's about G of 13 or so. But we limited ourselves to GRVS of 12 here for DR2. But now with in DR3, we've now got a year's worth more data, and so we're able to push fainter. And so we're now going 2 magnitudes fainter, down to GRVS of 14 or so. We're also expanding the temperature range for which we're deriving radial velocity. So in DR2, we limited ourselves to this particular range, which was essentially FGK stars. And now we're pushing into late M and to some hotter stars here as well. So as I've said, let me just illustrate some of the spectra here. So we're not looking at very cool M stars, although we are looking at the later type M stars, and so we are going to get some interesting looking spectra here with the molecular bands. We have the typical K, G, and F type stars that were in the previous release, but we're also going hotter to include A type stars, but we're not going as hot as B. So you can see the spectra here are dominated by the calcium triplet lines, and also and then as we go hotter, these start to disappear, and we have left with the hydrogen series here. So as I said before, there's a big step change in the number of radial velocities that are available. So here's the sky distribution of those stars. So unfortunately, I can't show you the new all-sky radial velocity map, which we've made, because we're really starting to be able to pick out different objects in that, but I'm afraid you have to wait for that. The radial velocity precision is given on the right-hand side here. So I haven't shown it here, but in DR2, the precision was about 2 kilometers per second or so at GRVS of 12. So we're able to, improve on that. And then going down to 14th magnitude, we're a little bit, or just slightly worse than 6 kilometers per second is the precision. Then so that's for FGK stars. Going hotter, is the performance is shown in the blue line here. So you can see that this is really shooting up as we go fainter, and so for stars hotter than 7,000 Kelvin or 7,500 Kelvin, we only go down to 12th magnitude. So you can see that in terms of DR2, DR2 is forming about 20% of the data, and about 3/4 of the data is going to be for new stars. Now, in terms of hot stars, we didn't include radial velocities for stars hotter than 7,000 Kelvin because they had very large systematic errors, and as large as 50 kilometers per second. So this was because of they're deriving their astrophysical parameters. So the use of the astrophysical parameters derived from other parts of Gaia for these hot stars actually was erroneous, and so we were actually trying to cross-match our hot star spectrum with a template that was actually of a different temperature, and then we were getting these biases in terms of the radial velocity. So in DR3, we're redetermining the astrophysical parameters ourselves from the RVS spectra, but as the plots show on the left-hand side here, that doesn't fully remove the systematic errors. So before is on the top here, so the Gaia radial velocity against the ground-based. This gives the bias here, and then on the bottom you can see that we can correct that bias in some temperature ranges, but not all. And so this correction factor is not actually being applied to the data, but it's being provided to the user so that the user can decide to use it or not. So for the first time, we're going to have V sin I, or V broad. So this will be the largest ever catalogue of rotational velocities, as well as the largest ever catalogue of radial velocities. So we're calling it V broad because it doesn't just include the actual rotational velocity of the star, but also includes the macroturbulence and template mismatch, which still could be a factor, and some residual instrumental effects. So of course, we're limited by the resolution of the spectra, which is just a medium resolution spectrograph. So 11,500 is the resolution, and the performance here is shown. So we're able to measure the rotational velocity over a wide range of temperatures, but most of them are in our classical FGK range. So we're also measuring, having measured our own magnitude from the RVS spectra previously, and just used that internally, we're now publishing it for the first time. So there'll be about, so that's going to be, that magnitude is going to complement nearly all of the radial velocities, so 32 million of those. And this is just showing you the magnitude range over which that the passband is being defined. So we're actually getting down to a few millimagnitudes in terms of uncertainty of those magnitudes, until we get towards the faint end and when we really start to run out of signal. As Ted said, the RVS spectra are going to be released for the first time. So we actually produced 33 million spectra, because this is how we've been able to measure the radial velocities. But it's the choice of CU8, the downstream CU, of which ones to publish. So in total, we treated nearly 3 billion CCD spectra. And offered in the end 8.5 million actually to CU8, having done a signal to noise cut. So you can see that the signal to noise from 45 looks very nice. 15 is starting to look problematic in order to derive atmospheric parameters from, and so that's the cut that's been made. And so 1 million spectra with a signal to noise greater than 15 will be provided as part of DR3. And so really that's just a taster of what's to come in the future. So in terms of what CU8 are going to do with the spectra, so this is actually a movie that I've grabbed from the web, but I'm not going to play it because actually I find it a little bit distracting. So so looking at the normalized spectrum against the wavelength range here, you can see that color-coded here of all the chemical species that CU8 are going to measure the abundances for. And so you can actually see that the spectra are very rich in terms of these chemical elements. And so DR3 is really adding the chemical space to the kinematic space that's already been established from DR2. In addition, in the box here is the diffuse interstellar bands. So these actually aren't features that are in the stellar atmosphere themselves. These are ions that are in the interstellar medium, which are absorbing the starlight as they come through to us seeing them. And so measuring these diffuse interstellar bands allows you to map essentially the dust in between yourself and those stars. And so this is just a taster of what can be done with the mapping of that of spectra and seeing how those diffuse interstellar bands, how their equivalent widths are stronger in particular directions. So this slide summarizes the CU8 harvest in Gaia DR3 overall, but I'll just pick out what's coming from RVS. So in addition to the abundances which I showed. There's the astrophysical parameters, so the temperature, log G, and metallicity are coming from the spectra for nearly 5 million stars, and then the chemistry, hopefully, for most of those stars. There's also activity index in terms of the calcium lines being filled in, so chromospheric activity, looking at emission line stars and hot stars and binaries, and of course this 2D map of the total extinction. Another contribution is going to be just a few epoch radial velocities. So we've got all the epoch radial velocities that have been from this processing, and they've been used by CU7, the variability coordination unit, and they've chosen to release around 2,000 sources with which have a time series of radial velocities. And so these are for so in Cepheids here you can see it's just an example of so the G magnitude, how that varies with time. The BP magnitude and the RP magnitude are all quite similar. And then you can see the radial velocity time series. So this all adds to the increasing the confidence in classifying these stars. And so many of these photometric and radial velocity time series curves will be released as part of DR3. So these are examples of our Alare stars. So you can see the BP in blue, the G magnitude in green, and the RP in orange, and then the radial velocity again at the bottom. Just to give an example of a few of these. And then finally, in terms of binaries, Gaia is going to CU4, the processing unit that is looking at binaries, are going to look at astrometric binaries, photometric binaries, but also spectroscopic binaries. So I'll just highlight here that there's going to be 100,000 spectroscopic binaries. So it's SB1s, so a single-lined spectroscopic binary, and several thousand double-lined spectroscopic binaries. So the double line binary is just illustrated here. So the radial velocity against phase of two different components that you can see, and so at different phases you can see two sets of lines or just one as the source moves around as the two sources move around each other, and cause the changes in the spectrum. So I'll summarize here. Sorry, I think I might have gone on for a little bit longer than I said I would. So just to say that the Gaia's radial velocity spectrometers contributed to the revolution of Gaia DR2. I've shown you a little bit how it's done that. And I'll look forward to show you that there's even more data and different products expected from RVS in Gaia DR3. So that's coming in a few months. So hopefully, and I've just reminded you about what's available already in Gaia's early data release 3 that came out back at the end of 2020, and that was the astrometry and photometry. And so a bit like in DR2, Gaia's full data release 3 is going to allow you to combine the astrometry, photometry, and the radial velocities all together. And so hopefully the Gaia revolution will continue, but that will be down to you guys to use the data and to do some fantastic science. So thank you very much for your attention.
Thank you very much, George. We'll give you the virtual clap that everyone's
yeah.
Okay, so if anybody has a question for George, please put your hand up, or feel free to type it in the chat if you don't want to speak up. We've got a couple of hands up already. So we'll go with JJ first, and then we'll move to Scott. You're muted, I think, JJ. You. Somehow we lost your sound. Maybe it's just me. We'll let you figure that one out, and we'll go to Scott's question. So go ahead, Scott.
So one of the characteristic features of proper motions is that the accuracy of the proper motion goes up like some large function of large power of the time span of the observations. What's the ultimate limit on how long Gaia can keep operating? Is it money from ESA? Is it some expendable? How long could it keep going?
Yeah, so it is. That's a good question. So yeah, it's the it is the consumables on board. So it's the micropropulsion that's keeping Gaia in this kind of continuous skid that controls the scanning law, and so that has been estimated to come to an end in about 2024. I think it's the best estimate. So so if that's how it goes, then 10 years is the baseline. The best baseline we can hope for Gaia data, and so yeah, that will, as you say, provide the sort of the limit on the proper motion.
So JJ has typed this question now. He says, I was wondering if you could compare the ability of Gaia to constrain the properties of stellar binaries with SDSS apogee.
So yeah, I'm not very familiar with apogee, I have to admit, but the so what can I say? So I think Gaia will certainly give you large numbers. So I mean, let me come back to my so here. So I mean, so we've got so Gaia's got the advantage of having the astrometric component, the photometric component, and the radial velocity component. And so with apogee, I think it's just the spectroscopic component, and so being able to combine all this information together, I think would probably gives Gaia the edge. Although I know apogee has much longer wavelength range and much higher signal to noise in its spectra, and so the radial velocity precision of apogee is much greater than Gaia's RVS, and so I would say getting a handle on the full range of binary parameters is probably maybe better achievable with apogee in terms of lower amplitude binaries, I would say, because with RVS, in terms of the spectroscopic binaries anyway, you're limited by your transit radial velocity precision, which is I think an order of magnitude, if not more, less precise than the apogee data.
Then yeah, I guess Gaia is killing it in the wide binary game as well, right? Which is an interesting
yeah, although that's so yeah, I guess it's complicated to match it all up. That's the so at least in terms of the data processing, I think that's yeah, so I think we're basically leaving that to the community, I think, to try and find those binaries.
Okay, we are past the hour now, so people might start filtering out, but we'll continue the discussion because I think it's interesting. But we have a question either from Nej Frankel or Hans Walter, who are a combined force today on Zoom, so I'll let them shoot.
Yeah, I guess I raised my hand. I had a question also about binaries, right? Gaia is also multi-epoch spectroscopic survey. As you pointed out, in the most generic way, if a star orbits something else, is that the radial velocity variations will be published as variances in the radial velocities measured. So in Gaia DR2, if a star had very high radial velocity variations, it effectively got censored because, I think for good reason at the time, if the variance of radial velocities was above 20 kilometers a second, then it wasn't published. Will that be the same in the DR3, or if a star orbits somebody else at 150 kilometers a second, this will show up as a very high RV variance?
So yeah, so the limit has been increased to 40 kilometers per second for DR3. I know that's yeah, that may not be what you want to hear, but yeah, that was the decision that's been made. I suppose it's the difficulty between trying to have some sort of quality cut and not publish too much rubbish, if you like, because we have a lot of spurious radial velocities internally, and so trying not to swamp the community with rubbish is what we're aiming
I have
for.
sympathy for that. Thank you.
But, one man's trash is another man's treasure. There, right?
Yeah.
We have another question from Harvey. Feel free to.
Hi, can you say a bit more about the parallax systematics? I mean, that's been a real issue for earlier releases.
Yes, sure. So I don't think I say much on it, but so from let's get back to the astrometric part. So so this is just the precision course that I'm showing on the y-axis here, but I believe the systematics have halved roughly, I think, going from DR2 to EDR3 in terms of the 0 point that's been published that you should use as the correction. I'm afraid, yes, I'm not an expert on this, so I can't really say too much more on that, I'm afraid. So so Lindegren did a paper, part of the EDR3 suite of papers, talking about the parallax biases and the 0 point. So yeah, I'd point you to that paper. I think.
Okay, thank you.
Cool. Any more questions for George? Okay, I guess maybe we should let George go, seeing as it is late for him in the UK. So we'll give you another quick Zoom round of applause.
Thank you very much
for kicking off the SSSSSS. Oh, I think there may is it. Oh, I thought there was. I think Hans Walter raised a hand and then decided to applaud you instead. Yeah. so you managed to escape that one. But yeah, thank you very much, George. We'll meet again. The SSS continues into the next few weeks, so keep an eye out for the next talk, guys.